Yeah. And now the second, yeah, I'm also in SC7, so I'm aware about this. Okay. Okay, so we can start. We have a very nice session, the second afternoon session, which is opened by invited speaker. I have the honor to introduce you the invited speaker, Professor Dr. Rüdiger Hofer. He is coming from the University in Bochum, from the Faculty of Civil and Environmental Engineering. Professor Dr. Rüdiger Hofer studied civil engineering and obtained his doctorate in 1996, and at the Ruhr University Bochum in 1995 till 1997. He was a visiting scientist at the Danish Maritime Institute in Copenhagen and the University of Florence as a scholarship holder of the European Research Framework Program. From 1997 till 2003, he is a senior structural engineer and today a partner in several specialized engineering companies. Since 2003, he is a university professor for wind engineering at the Institute for Structural Engineering at the University of Bochum. Since 2009, he is also a designer review engineer for structural integrity and fire protection. From 2011, member of the European Standard Committee STC 250 SC1 and a National Mirror Committee at DIN. He is an expert and is working on the new generation of Eurocodes, and as we will see from his presentation, he will going to give us some insights in the new and second generation of Eurocodes. Besides this formal part, I would like to give my personal also note to this introduction. Professor Rüdiger Hofer is a STEAM expert in the field of wind engineering, and his institute has a great tradition in research and testing with this famous wind tunnel, which has performed many, many interesting research studies. He is an active member, as I said earlier, working on the Eurocode, and last but not least, he is the great friend of the Faculty of Civil Engineering and honorary member of MAS. So the floor is yours, Professor Hofer.
Thank you very much for your kind introduction. Yes, to be an honorary member of MASE is always a big joy. Every 2 years I'm allowed to come here and participate to your esteemed conferences. Ladies and gentlemen, it's now late in the conference, and I think my task is here not to produce maybe too much delay. Also, I wanted to say we have heard and attended very, very ambitious lectures. Especially the invited lectures have brought us to visions and have shown us how exciting our field of activity is. My presentation brings us a little bit back to, let us say, everyday's work, as we are every day guided by codes. And codification is something where a lot of experience is in, and therefore I'm also happy to be there in the circle of experienced experts in the code work. I would like to inform you briefly about future European standards. Please also take attention to the subtitle General Actions, so it is something about actions. And I'm doing this as Vice Chair of TC 250 SC1. So a short overview shows us some remarks to the priority topics of the updates, then procedures in the update of the structural Eurocodes. Short remarks will follow on various parts of the general actions part. And I also would like to comment on the coverage of climate change issues, and then some very short conclusions. Let me start with this overview. What you can see here is the full program of the EEC1, the Eurocode 1, and the green marked parts will be commented on during my short presentation. I hope it will be short enough. Please consider that here have been done a lot of changes to the different parts, but also a totally new part was created and compiled, and that is part 1.9, atmospheric icing. The others are also available now in the different national standardization boards, I guess. Let me quickly guide you through the priority topics, and this is, of course, something of political background. What was said there in the first instance, that the drafting of the new Eurocodes, the second generation, should enhance the user's confidence. The Eurocode family sees itself as working with state-of-the-art documents, and I think this is also true. All the effort was done to produce modern codes. It shall be user-friendly, and the ease of use aspect was emphasized, and that is something which might have some potential to be improved at this point. The harmonization across member states, that was a specific point. The harmonization means that traditional methods from different countries might not be included in the second generation, and then of course big fights start at the national standardization bodies, because that means always a big impact in the country when an existing procedure is not any longer in the background of the code. But we have taken attention of these and paid attention to this point, and also considered nationally determined parameters to be open enough to include those things. Sustainability consideration, there was an invited lecture just before about sustainability aspects, and that was, I think, a vision. It was a vision, and it clearly shows a way which could be possible. Of course, the Eurocode, also the developing of Eurocodes, that is a state of the art, so that is not a vision that tries to work with it with existing methods. Climate change consideration are included, and also more attention is paid to existing structures. So let me very quickly give you just a small overview about the tremendous number of why not? Something doesn't work. Okay, not this thing like this. The tremendous number of committees in the game. So what you can see here, the background is the ISO codes that are delivering input. Then we have the CEN family combined from the TC, the technical committees. So for example, TC 250 SC1 is our committee. SC1 is a subcommittee number 1. Working groups, horizontal groups, ad hoc groups, all this committee work is there, and sometimes it seems to work in an authority with all these departments when being in that area. But the real problems are discussed in these smaller circles. The working groups, the task groups, and the project teams, PT, project teams, and of course also in the national standardization bodies, where all the results are then presented. And the national standardization bodies, they have the task to work with this. So for example, in your country that would be the ISRM, and that gets the results and then reflects on it from the view of this country. And then it is in the framework of the inquiry phases published and documented to the professional public. That is the light blue circle on top. And the professional public, of course, should be organized. And what could be better in your country, here in North Macedonia, to have for this task MASE. So MASE could be the structure to discuss these codes and give experts' recommendation to the ISRM. This game has been trained for many years, and so I took the liberty just to give you a short overview of what is the background of the committees here. You can see that the work was predominantly guided by the British before. although they left the Union formally, they are still the ones who, due to the experience and the good structure and the good ideas, are in the management and also in the advisory board. The coordination group has its seat there, and TC 250 has a variety of contributors there, and you can see that many countries are contributing and some countries not. And that is, of course, a question of resources, a question of a tradition as well. I must really say, and this is my personal opinion, that the number of flags to be seen here could be really increased. The procedure itself started in 2010 with the mandate M515, and now the X at the end of this time beam shall be 8. So 2028 is the date of withdrawal of the existing Eurocodes and the implementation of the newer one. That is, of course, an estimation that depends on many, many things. I think the European process will be ready then. The implementation in the countries is another question because national application documents must be produced, and that, of course, will bring a lot of additional effort and time will be used for that. After this introductory words to the procedures, I would like to go a step forward with some remarks about the different parts, but that shall be not take too much time. So we have there the Eurocode 1 Action on Structures Part 1.1, and that is the part that we all work with every day, I would say. That is the specific weight of materials, self-weight of construction works, and imposed loads for buildings. I think this is also program in any course in civil engineering, bachelor or master level, and there we have now a new code as a proposal that has not many pages, 27 pages, and 15 pages for one single annex. The left side of this table is organized in the way that the chapters of the main document are written, and written in white color are those documents or that chapters, sections, which are following a regular structure, so the headers are always the same. In all parts of the code, EC1, you will find this introductory chapters, and then it is case specific. For example, here, specific weight of construction and stored material, self-weight of construction works, and then our classical range imposed loads on buildings. 27 pages, not too much, and the annex about the mean values of specific weight of construction materials is only 15 pages. I think there will be no problem to work with it. Some adjustments and enhancements have been done, but these are solely of editorial, maybe a little bit more than editorial changes only. There are also new values due to the fact that, for example, imposed loads are increased, especially for vehicles. Vehicle weight is growing, especially due to electric cars, also helicopter weights, also garage loading, things like that, and further adaptations and adjustments are enclosed. But I think that will bring no problem, and there are a lot of NDPs so that one can fix such a new code with own knowledge and own measurements in the country. Snow loads, there was more discussion here, but the extent is also not very large. Again, the first 4 chapters or 5 headers in the regular schedule, and then we have here design situations, modeling of snow load on the ground, snow loads on roofs, local effects, 32 pages. It follows again the classical pattern, but we have here introduced also, so if I say we, then the working group which was responsible for that, new models for snow loads on the roofs. And this new model takes account also about the question, is the right thing to use the characteristic value of snow load on the ground, or do we have to look for something more forwarded, and that could be, for example, the question about the size of the roof. If one has a very large storage hall, then the snow load on the roof must not any longer be reduced with the shape factor 0.8, but now there is a stepwise increase to 1.0 due to the fact that there have been building equipment developments to insulation, and also the pure size of the building will avoid snow drifting, so that 1.0 is the right value. That has been discussed many times and will give, of course, some impact on static design. Of course, the building stock has not been changed then, but if new buildings will be erected, that has to be considered. Exposure coefficients are a little bit adapted, new models for pitched and gable roofs, and also abutments have been treated. So also nothing serious, but maybe there is the necessity to review that in the national standardization body under the and looking at reflecting comments from the expert public. Much more has been done in the wind loading, and that, I must confess, was also violating a little bit the principle of ease of use. You can see we have now only 42 pages in the main part, where it was before nearly 100 pages, but that was just a trick because all the data, tables, coefficients have been moved to the annexes, and therefore the annexes now has 266 pages, so we have a 300 page document, and I must really say the local standardization bodies will have a lot of work to fix that. Maybe you can see here that most of the annexes are informative. That means these are recommendations, and the national standardization bodies are free to formulate adaptations, also to formulate completely new annexes. But the annex as they are, they fit better in the procedures and are also reflecting the state of the art. There are only a few normative annexes. That means when accepting this code, one must use these normative annexes, otherwise the code is not applicable. So, for example, we cannot apply Chapter 5 or Chapter 7 wind actions when not having at hand some aerodynamic coefficients, and these are given in the annexes C, D, and E, and so these must be normative. But in this annex again, at several places, there are nationally determined parameters. So, for example, when measurements are available for certain structures, then it is possible for a national standardization body to change also piecewise coefficients there, if it is allowed by a nationally determined parameter. So the pure extent of this code will be problems when creating the national annexes. But let me please at least give you some examples for that and some guideline, and also maybe this is also some motivation to get into the topic. The extension of the scope of the application of the standard has been increased to 300 meters height. So one could ask, is that really necessary? Yes, it is, because we see that in the growing cities in Central Europe, we have building heights that really come to this limit. The highest building, office building in Germany has exactly 300 meters, and buildings in Great Britain could not be designed before based on the code models for wind, because these wind load models were only up to 200 meters. And that was, of course, a deficiency of the old code on wind loading, and now it has been extended to 300 meters, and by this also created some interesting comparison. Many values of the aerodynamic coefficients have been added. So, for example, we can easily believe that buildings in reality are not rectangular blocks, but of course with a lot of different shapes, and that has been implemented. The atmospheric icing will now be included, and there are also wind effects on silos and tanks and cooling towers, by the way. Let me give you an example for the importance of the first point. So it has been added a quite complicated new wind load model. And of course the discussion about that was also aggressive, because the traditional logarithmical model, which also is studied by students in the bachelor courses, has been extended by an additional parameter and made adaptable to the theories of Dives and Harris. These are two meteorological experts who have evaluated atmospheric behavior, turbulences and mean velocities over height, and brought up new models. So of course it is a big step for a code to adapt such a model, and that is done only if that has a good reason, and the good reason can be shown on the next page. And here maybe I should have done that in another scale, but what I would like to ask you is to compare the blue, the gray and the orange curves in the four diagrams. And what we can see in the diagram left, upper line left, that is a comparison between the blue and the orange curve. And this comparison shows us how the logarithmical model performs with respect to a meteorological model, namely that from Hellman. And that from Hellman is well approved, and can be seen as a reference model. By the way, it was also adapted to the German code since 1986 and never left apart. And we can see that at this terrain category with a low roughness on the ground, the blue and the orange curve fit well together. Well, this is not surprising, because the logarithmical model in first instance reflects small roughnesses on the ground. So let us say green grass near to the coastline, flat terrain, no houses, low bushes. That is terrain category 1. And that was developed by Professor Prantl from Göttingen in 1905 as a good profile. The first time it was available to know something about boundary layers, and that was implemented immediately to regulations. And so the Hellman profile is the verification by meteorologists in the atmosphere. That fits well. But if we go then, for example, to terrain category 2, which is the standard terrain category, I would say it is terrain around airports, or in flat terrain with houses and bushes and some small, let us say, industrial buildings. There we can see that now the picture is different. There is a deviation as well from the orange curve, the Hellman profile, and also of the gray curve from the logarithmic profile, and that has been adapted now here. The more roughness we have, the higher is the difference between the theoretical logarithmic curve and the validated curves from meteorology, and therefore now, using this new wind model, it is possible to extend the code to 300 meters height for all those countries who have not automatically at the beginning used the Hellman profile. And in Germany we are happy to have that done, and we must now not change any calculation procedure, but many countries should do now for higher heights, and my recommendation is to make a comparison between Dives and Harris and the Hellman profile, and you will find out the Hellman profile is simpler. So maybe that is something which the standardization body will find out. Well, here I can be a little bit quicker. It is an overview about a totally new group of aerodynamic coefficients, namely that are global coefficients. They are intended to be used when quick calculations of wind loading effects on foundations and stiffening systems, general stiffening systems of buildings are needed. In your country, there is always, or in the countries where seismic activity is much higher than in Germany, there is always a lot of horizontal stiffness due to that point. But in northern and middle European countries, it is always a question which part of loading, which horizontal type of loading gives the decisive values for stiffening. And for example, for bridges and for high-rise buildings in our area, wind is mostly the relevant parameter for horizontal stiffness and not seismicity. therefore, it is important for industries and consulting offices in that area to be able to pre-calculate quickly foundations and stiffening systems. And of course, also varying shapes of buildings have been considered in the new code. That are patterns which exist, which really exist. So one had done some work to make it a little bit more abstract, a little bit more general, but these are building systems which really exist, and not only in the plan view or in the section, but also forms like this are now possible and regulated. And a special effort has been done for dynamics. So we have the phenomenon that wind excites buildings to resonant oscillations, susceptible buildings with low damping, typically high-rise buildings, bridges, and towers. And there the standard structural factor CSCD, which in the same moment considers a size influence, which is a favorable effect, which lowers the load, and a dynamic influence, which excites to resonant oscillations, which increases an equivalent static load. Both is used together, and that we have now put into, let us say, a little bit adapted procedure where also mode shapes with changing sign can be considered now, and that is the CSD method, which is now in the informative Annex G. And of course, communities must now decide whether to adapt it or not. It is an informative annex, but it is an offer and it is a development of the formerly relatively unflexible procedure. Annex J was a special wish from the British for steel lattice towers and guide masts. And then we have there three new annexes, K, L, and M, and that also takes position with respect to very modern approaches like numerical, also CFD methods, numerical methods in flow dynamics, which are more and more used, and that needs guidance, that needs regulation, because there are already at least two big design programs that allow for that, and that must be regulated, of course, because it delivers also non-validated results. This is not a topic of today, I just wanted to make this remark. Also, the derivation of wind speeds from measurements at meteorological stations is now commented on in the code, and probabilistic models for wind effects as well. And of course, all these annexes are informative and are used to inform the professional public. Another thing is very interesting, which cannot be solved so quickly. That is a European wind zone map, and this European wind zone map was intended to be also implemented into the code and then gives possibilities to have only one wind zone map for all Europe. Apart from the problems we have nationwide already, for example, when bridges are crossing borders, or bridges are done at positions where no meteorological stations are, then one runs really in problems. We are now working at the new Sava Bridge in Belgrade, and there is a similar case. The meteorological station is a little bit apart, and it's difficult to define a fixed wind profile there, also because it is a river valley, and canalization might occur, and I hope to be able to write about that, inform about that a little bit later. But a special point gives a little bit of concern, namely the jump of characteristic wind speeds at national borders. Of course, that cannot be. That can be only in certain cases. And it is a little bit not, I would say, please take it with the right sound that I used the Danish example. So, for example, in Denmark, we have big differences between Germany and the Danish wind speeds. Maybe you can see it the best on the right-hand side. There we have our wind zones 25, 27.5 and 30 near to the border, and the Danish have lower wind speeds. Although when thinking about North Europe, this is the area where there's a lot of wind. And of course, I discussed a lot with experts there, namely Svend Ole Hansen and other people from that country. And they found out that part of these measurements have been done in 85 meters height on platforms and bridge pylons and then calculated down on 10 meters height, whereas the Germans do the other way around. They measure on 10-meter height and then evaluate it there directly. But this is something that must be harmonized in Europe because we have really problems to that. I was also a witness and expert on working out a written paper for a court about damages near to the German border in Denmark, and there always came out that maybe the wind velocity was taken a little bit low, but I have the feeling that is on a good way, so we will find their harmonization in near future. Other places are also present in Europe. So, for example, the borders between Great Britain and the Netherlands, Great Britain and France, there are all jumps in the wind profile, a big problem for a European wind zone map, and that will take some years until that will appear. Another point is vortex shedding. Vortex shedding is something that brings stacks and chimneys really in danger, not by sudden cracks and failures, but mostly by fatigue. And we have there two different vortex models in the current code. And these vortex models have the following features. On the left-hand side, you can see model number 1, or the results of model number 1, shown in the following way. On the abscissa, there are observed values of oscillations of chimneys, and on the ordinate there are calculated values used the respective code procedure. On the left-hand side, procedure 1, on the right-hand side, procedure 2. Procedure 2 is a spectral method in the frequency domain. Procedure 1 is a correlation length method in the time domain. And when calculating observed chimneys, then the result should be on a diagonal in the middle in an optimal case. Of course, it's not the case. Here we have hit rates where there is a scattering around, but what makes a little bit of problems are many values in the lower part of the left diagram. That means here predictions from the code are not on the safe side. And this is not so, only a few. On the right-hand side, it is method number 2, and the accumulation of results in the lower part mean that it is far on the safe side, so non-economic. So here we have a problem. Industries like left-hand side, owners like right-hand side, and we must find a compromise, not a compromise, we must find the right solution here. And we did that by getting one of the methods out of the code and fitting the other one by a lot of investigation which has been invested, especially, again, a Danish laboratory was contributing there, and also German laboratories, including our own laboratory, and the result is now offered to the public, and there should be some comment. Now, let me speed up for the thermal actions. Not much to be said. I can jump here and immediately just point out that characteristic temperature components and temperature differences have been found. The new thing is here that certain bandwidths are introduced, which make, again, effects for bridges with respect to their temperature dilatation. And these uncertainties is, again, a matter of I would say, discussions in the national standardization bodies. It's quite clear that these uncertainties are higher where the temperatures are higher, so there is some gradient from the north to the south, and every national standardization body must find its own solutions. I jump over this slide and go to the accidental actions. More emphasis has been put on consequence classes, and there is also now a new annex on debris. Internal explosions have been always implemented. These are gas explosions in building, housing, and the compatibility with the basis of design code, Eurocode 1990, has been increased. And then there is a totally new course, a new part, and that is atmospheric icing. That was designed after the ISO pattern from 2001. We have again glaze and rime ice classes. I think that is known to most of the engineers and has been actualized and a little bit amended here. There is now a height factor for glaze ice, and the models are left open for the national annexes. There is a lot of flexibility. Just to make you remembering, these are the diagrams, tables, and also pictures for that. Glazing and the other type of and rime ice, that is a danger for transmission lines and things like that. And by the way, I should say that we are in the moment going with a big project in two climatic wind tunnels. There is one climatic wind tunnel again in Denmark, so there's a lot of cooperation with Denmark. In Lyngby, they have a big climatic wind tunnel. We are going there to do a study on atmospheric icing. And the second wind tunnel in Europe that is working with that is in Prague, Czech Academy of Science, and also there will be done comparative experiments. Now we have seen the last three codes commented on, or three of the codes commented on. They have to do with climatic actions. So the question is immediately there, climatic actions has to do with climate change issues. How can we tackle with that? And here, of course, grows uncertainty tremendously. And that, of course, is also something that has to do with this fuzzy question that I did to Professor Katzi this morning. Markov chain and Bayesian procedures cannot be used here because the uncertainty is too big and it has no clear pattern. This is an open question how to tackle that. What happens is that flooding can be seen in a tremendous way in your neighboring country, Greece, just in the last days and some weeks ago. Tremendous effects. We can prove that with high confidence intervals, statistically also. A change of the extreme values can be seen, clearly visible, can be proven, and we cannot deny that this effect is there, especially regarding flooding. By the way, I did not comment on the new code on waves and currents, but in the new code for waves and currents, these parameters describing these effects must be implemented. And that is a little bit far from state of the art because the predictions are uncertain. We have seen, this for example is in Germany, we have seen increased icing, although temperatures are higher than before. Icing is not lower, and also snow loads are not decreasing. That has to do with the humidity content of wet snow. Also here, the characteristic values have high uncertainties, and temperatures is, I must say, the value that can be measured best, because there only simple sensors are necessary, and also long data bases are available. Here we find some example from, again, from the Czech Republic, and this was done by the Klöckner Institute in Prague, and they found out that they have to increase their surface temperature and the temperature differences for buildings. When considering wind, we have to face a certain problem. From all climatic sources of loading that we know, wind is the most unknown, the most extreme wind is the most unknown one. Not only extreme wind, also everyday's wind. We are not sure if the quantity of storms will grow. We are not sure if the extreme values are growing in the moment. We don't know if the number of tornadoes is higher. I have some slides about that, but I had to sort it out. What we know is that new effects become more frequent, namely the incorporation of thermal effects into deep pressure zones. And what I mean is, again, a nice example where we can see some storm measurement here. On the lower diagram, you see two curves, a green one and a violet one. The green one is a 10 minutes mean value over time, and these are several hours and days measured here. And the purple one, these are gust wind speeds, so those wind speeds which are taken for design, not the mean velocities taken, but the gust wind speeds, times a statistical factor. And of course the question is, what is the statistical factor? For a pure mechanically generated turbulence like a deep pressure wind zone, one of these deep pressure zones that come from the Atlantic and then covering Europe and producing the storms, that is well understood. We know the gust factors which belong to that. It is something between 1.4 and 1.7. But here we can see that there was a factor between the green curve, the mean value, and the measured, not estimated, the measured gust wind speed of more than 2. So absolutely unusual, and it was not clear what this was. And after some consideration, it came out that that was a thunderstorm, but a special thunderstorm, a downdraft, implemented in the first vortex of the deep pressure zone. And these effects are temperature dependent, and they become more frequent. So that is a very complicated source for a new phenomenon that comes up more often. And so I guess that the gust factors have to be improved. And that is also something where a lot of research is ongoing. The Italians, Giovanni Solari, has taken an ERC grant on that and formed a big laboratory in Genova. Very unfortunately, Giovanni died 1 year ago from a disease, and his team is ongoing with this research, and also other groups in Canada and in the United States, they are going in this investigation, and that will change our gust factor surely. If we look to predictions of wind speeds, which are available of extreme wind speeds, not the number of everyday's wind speeds, then we find this picture. That is one with a 95% confidence interval after the student t-test. And what you can see here with yellow colors, that is a slight increase of wind speed, of extreme wind speed, and blue color is lower wind speed, and that is a prediction to the year 2100. So within the time frame for which we plan important structures. And, but the difference is not so large, so we can see that in Europe we come up with up to 0.75 meters per second more. That means only a very, very moderate corrections of our characteristic values. That will be absolutely different for other climatic actions. So let me come then to a conclusion for the climate change coverage. That has been proposed by a document from TC 250, and there will be introduced a factor, but this factor is, after my point of view, pure formalism, because this factor has no life inside it. There is no number for this factor. In the moment, the factor is 1. It's only a form to deal with it in future. And I think there much more work of enthusiastic, especially young engineers is needed because we cannot come up with such a thing and just say national standardization body, find your factor. Then it's not very interesting to do that. So to end my short presentation here, I would just to give you an overview about the codes I was reporting on. The status is that the inquiry phase for these parts are running, with the exception of wind actions. That is a year later due to the big extent of new procedures which have been implemented. The inquiry phase means now opinions and comments from the expert public is asked for, and then shall be formulated as a comment to the project teams, or better said, to the working groups, and then it shall be implemented or not, such a proposal. We have found out that user friendliness was not put into question by the test users and also by the publics that got already the codes. The harmonization was also very welcome, with the exception of very few procedures. Especially positive was accepted that the codes are open for new materials and new methods. So that was commented very positively on. The climate change issues were not commented at all because nobody knows numbers. And at the end, I must say that your input as people who work every day with codes like this is the most important thing, to discuss the codes now after the experts have made a proposal, and every opinion is very welcome to the inquiry phases. And if your country or your group is not part of an inquiry team, then I could only invite you to send on the short draft just a comment to me myself, and I try to bring it into this committee, and then maybe at least the opinion is not lost. So, production of national annexes is the work of the next years, and with that I can close, and thank you very much for your attention.
Thank you very much, Professor Hofer. Thank you for the insight in some of the parts of the second generation of Euro codes, and your German, let's say, national annex is part of what you plan to implement. As far for the implementation of the second generation, you put some X at your first slide. I will try to give you a solution. Maybe it's 4, number 4. So the X is 4. We'll see, but it will be very soon, as I heard.
40 or 4?
Yeah, I think it's more like 4. But anyway, now I will ask the audience for some questions, please.
May I just make a comment to your expectation? This 4 does not mean of the current code family. This X is for the future code.
Yeah, exactly, for the second generation. This is what I thought. Yeah.
And that will be larger than 4, I guess.
Questions?
Yeah, what to put as a question for such a mass of regulation, I know. But comments are also welcome.
So it's obvious, Professor Hofer, that Europe is not so united with the winds as you showed us. So is it going to be a step forward in this regard, or you expecting that everybody will keep their grounds?
Yeah, I think it is not. It has a good reason why the part number 4 is the last one in the inquiry phase, because there have been already a lot of discussions, and that will be ongoing. I guess that a lot of countries will use the old national annexes for all the informative annexes instead of formulating new ones. But this is only a personal guess. I would not know how to come forward quickly with that. But this is really a problematic case, I must say.
Okay, if there are no further questions, we'll invite the president of MASE to hand you in the certificate. Yeah.
Before we continue, I would like to ask the presenters to try to keep in line with the time frame, not to gain additional delay. Our next presenter is Radomir Folic from Faculty of Technical Sciences from Novi Sad. He will present a paper, New Tendencies in Designing Durability of Concrete Structures, that he wrote in co-authorship with Zoran Brujic.
Thank you, Mr. Chairman. We prepare this presentation in English, but I will speak Serbian to be faster. Poštovane koleginice i kolege, ja ću u uvodu reći nekoliko reči o tim aktivnostima. Čuli ste kolegu Hefera da se radi aktivno na osavremenjavanju ovih naših propisa. Motiv za pisanje ovog rada je jedno savjetovanje Društva konstruktera Srbije pre 2 godine u Aranđelovcu, kada smo diskutovali o inovaciji propisa. Dvojica kolega iz jedne, da kažem, poznate evropske firme su imali primedbe da se brzo to menja, jer je pravilnik za konstrukcije pre 3 godine usvojen i usvojeni su eurokodovi iz prve generacije. Da podsjetim, 90. godine su bili predstandardi. Od 2002. pa do 2006. godine su bili prva generacija standarda, sada se radi na drugoj generaciji standarda. Kada se govori o betonskim konstrukcijama, onda treba pomenuti i Međunarodnu federaciju za beton, koja je nastala spajanjem Evrointernacionalnog komiteta za beton i Međunarodne federacije za prednapezanje davne 1998. godine na kongresu FIPA, Međunarodne federacije za prednapezanje u Amsterdamu. FIB radi takođe na inovaciji propisa i to skoro paralelno sa evropskim normama. Pa da pomenem iz prošlosti nešto što je značajno za ove mlađe. 1969. godine CEB je tad bio, znači Evrointernacionalni komitet za beton, je donao model code. To je model propisa za betonske konstrukcije u kome faktički daju neki okvir da bi nacionalni komiteti trebali da se uklope u taj okvir i da naprave nacionalne norme koje bi bile što bliže i saglasnije sa tim. I tada je došlo do jednog velikog problema vezano za trajnost betona, jer su neki, da kažem, uslovno rečeno statičari više uticali da se smanje zaštitni slojevi betona, jer navodno krak unutrašnjih sila se povećava, pa se racionalnije konstrukcije dobijaju i u mnogim evropskim zemljama je to i prihvaćeno, uključivši i raniju Jugoslaviju. Rezultat toga je naglo propadanje betonskih konstrukcija, naročito zavisno od agresivnosti sredine, naročito znači u agresivnim sredinama. Ono što je značajno, to je da je posle toga evropske norme i FIB su to popravile, pa čak smo i mi 1987. godine u pravilniku to značajno popravili i nije bilo tragičnih tih posledica po naše konstrukcije koje projektujemo. Zašto trajnost konstrukcija? Pa mislim da se to uklapa i u naslov ovog savjetovanja, jer je trajnost ono svojstvo koje je vrlo značajno za i sigurnost samih konstrukcija i racionalnost, i zbog toga je trajnosti posvećeno mnogo pažnje i u FIB-u i u Međunarodnoj federaciji za beton i u komitetima evropskim. Da pomenem samo da je nekoliko tih workshopova bilo. Prošle godine je bio jedan workshop, a ove godine poslednji bio 23. maja. I na tim workshopovima je puno novog rečeno i onog što će biti tek, jer ova decenija je zacrtana kao decenija u kojoj će ta druga generacija eurokodova biti objavljena, publikovana i usvojena u većini razvijenih zemalja. Mi ćemo verovatno malo kaskati kao što smo i u minulom periodu. I da pomenem da je uvedeno 10 eurokodova, 10. eurokod se odnosi na konstrukcije od stakla. Znači, staklo je uvedeno kao 9. je bila aluminijum i 10. je konstrukcija od stakla. Ono što se primećuje, jer sam sa kolegom Brujićem, mi smo najviše proučavali Eurokod 2, uslovno rečeno, znači evropske norme 1992 koje se odnose na betonske konstrukcije, ali smo takođe analizirali od Eurokoda 0, znači koji se odnosi na sve konstrukcije, do recimo Eurokoda 8. To je neka sfera koju smo i ono što se primećuje to je da za razliku od prve generacije Eurokodova, zgodno je da znate, približavamo se američkom konceptu performansnih stanja, projektovanja zasnovanih na performansama. Naime, Amerikanci su poodavno, naročito za konstrukcije u zemljotresnim područjima, uveli ta performansna stanja od trenutne useljivosti, odnosno od trenutne upotrebljivosti objekta do prevencije rušenja objekta, a evropske norme su tvrdo insistirale na graničnim stanjima upotrebljivosti i graničnim stanjima loma. Recimo za taj Eurokod 8 Mike Forde iz Patricel iz Grčke je naročito insistirao na tom upoređenju i na tome da možda treba usaglasiti sa Amerikancima. Znači u svim, uključivši i Eurokod 8 i Eurokod 7 i tako dalje, ovo što smo mi na osnovu materijala koji su bili dostupni i draftova koji su takođe bili dostupni, koji su sada na razmatranju da bi se to usvojilo. Da krenem od toga šta je bitno kod trajnosti. Znači, trajnost je do 80. godina bila zapostavljena, jer čak smo učili u početku da su betonske konstrukcije trajne, da su malte ne, zahvaljujući onoj činjenici da tokom vremena se povećava čvrstoća, a čvrstoća nije jedino svojstvo. I kada su počele sanacije objekata, naročito ovo što sam pominjao 71. pravilnik našao 71. godine, onda su ljudi shvatili da je problem vrag odno šalu, kako kaže naš narod. Šta je bitno za proučavanje trajnosti? Bitno je da usvojimo ili da ga poznajemo ili na osnovu statističkih podataka, praćenja, stanja konstrukcija, određenih konstrukcija u normalno određenom ambijentu i sredini koja može biti više ili manje agresivna i to je problem ponašanja i deterioracije, odnosno opadanja mehaničkih svojstava tokom vremena. To je jedna od najbitnijih kategorija da se taj aspekt, ovo je dosta sitno, ja ne znam da li može možda da se ovo poveća. Prosto, mislim, dosta dobar vid ima, bar mislim. Molim? A tamo, da. Pa evo, dobro, bolje ovako. Znači, šta je u sadašnjem predlogu? Postoje načini i dugo se koristi, to je preskripcija, odnosno propisivanje zaštitnih slojeva saglasno izloženosti ili ambijentu u kome se konstrukcija nalazi i to smo navikli na tako nešto, međutim sada je uvedeno i granično stanje trajnosti. S tim što granično stanje trajnosti je dosta dobro razrađeno za delovanje karbonizacije i za delovanje hlorida. Nažalost, za ostale hemijska dejstva, fizička dejstva, biološka dejstva i tako dalje, to nije učinjeno i nije razrađeno i to je jedan od problema koji ono što je sada značajno, to je da se uz ta performansna stanja potrebno su odgovarajuća ispitivanja. I za performansna stanja nema dovoljno podataka da bi parametri bili valjani, vredni, da se uvrste u analizu tih performansnih stanja. Zbog toga je ovaj dokument koji se odnosi na trajnost betonskih konstrukcija predvideo dve varijante. Jedna varijanta je da se koriste tabelarne vrednosti, ali ne tabelarne vrednosti koje su ranije bile, nego je uveden jedan novi pojam, otpornost prema izloženosti. To je ovo exposure resistance classes. Znači, klase otpornosti prema izloženosti. To je ono što je bitna kategorija i umjesto onih samo ranijih klasa.
2 minutes to finish. 2 minutes are left.
Znači, to je aspekt, taj nije kao ranije samo izloženosti u ovog ambijenta, nego i normalno da se Eurokod 2 oslanja i na evropske norme 206. Evo, ono što sam naglasio da se uglavnom razmatraju površinska korozija, karbonizacija i dubinska korozija i da se zadržimo na ovom. Predlog je, ranije je bilo ovaj deo, ja sad više ne znam, ima neki krug je bio, ovaj inicijalni deo, pa je naglo bio onaj FICO zakon, linarna, progresivni deo koji je bila linarna funkcija, nije više linarna funkcija, nego propagacija je zakrivljena linija gde se smatra da je tek kada počnu da nastaju oštećenja mnogo veća nego što su dopuštena ili prsline, tek onda se, ja sad ne znam kako se rukuje s ovim, znači kraj eksploatacionog veka, jer ove klase koje su novo uvedene nisu sad klase samo izloženosti, te klase zavise i od izloženosti, od kvaliteta betona i od, da kažem, mnogih parametara koji se uvode da bi se ostvario odgovarajući indeks pouzdanosti. Ovde je u pisanom radu je to detaljno obrazloženo, znači izloženost prema klasama izloženosti i veza klasa izloženosti. Za karbonizaciju imamo 8 klasa od 0,5 do 7, za hloride imamo 12 od 0,5 do 10 i zavisno od čvrstoće betona, od eksploatacionog veka, vidite ovde horizontalno piše eksploatacioni vek 50 godina, 100 godina, znači za te vrednosti, za te godine su eksploatacionog veka date te preporučene vrednosti. Šta je još bitno sem klase izloženosti i eksploatacionog veka, to je još nekoliko parametara, da li upotrebljavate zaštitu, evo Ading ima tu ispred naše sale zaštitne premaze i ostalo. Znači i od toga zavisi ta trajnost i normalno da se tako radi. Ono što je dosta pojednostavljeno, to je da se može, naime, moguće je da se opredelite za jednu ili drugu varijantu. Ako idete na proračun performansnih stanja, onda ćete imati malo više posla, ali ćete imati verodostojnije podatke. A ako idete na korišćenje ovih klasa i otpornosti prema izloženosti, onda ćete imati manje posla, ali nećete imati dovoljno racionalnu konstrukciju. Ono što se uslovljava kod proračuna, meni je rečeno, predsedavajući, moram da vam kažem da mi je rečeno da ću imati 20 minuti, zbog toga sam malo neke istorijske aspekte rekao. To mi je rečeno, rekao mi je predsednik Nakov. Brzo ću ja završiti, ne sekirajte se, to ću ja odraditi kako valja. Ono što je bitno, to je da, znači, minimalna čvrstoća betona je 25, da još jednom pomenem, znači da se može reći da je uvedeno granično stanje trajnosti vrlo kompleksno. Ono što je mana nije samo što je ono kompleksno, nego što vi možete samo za dva aspekta, karbonizaciju i hloridnu koroziju da pokrijete, a ne možete da pokrijete sve. Ostale stvari su vrlo fluidne i zbog toga se komitet taj opredelio da dozvoli da se koriste te minimalne debljine zaštitnih slojeva. Eto, to je otprilike ono što sam mislio da kažem, a ovo sam rekao zato što mi je rečeno da će imati 20 minuta zbog toga. Inače, ne želim da zadržavam.
Professor Folić, thank you very much for your presentation and for pointing out this problem of concrete. We can allow one short question from the audience. Thank you, otherwise we can continue.
Thank you.
Thank you.
So we go now to the next presentation. The topic is analysis of wind action on container stacks according to EC standards. The authors are Professor Todor Vacev, Daniela Đurić-Mijović, Miloš Milić, and Andrea Zoric. They are coming from the Faculty of Civil Engineering and Architecture from the University of Niš.
Can we start?
Yeah.
Okay. Mr. Chairman, dear colleagues, it's not quite comfortable under those reflectors. First of all, I would like to say that Professor Heffer gave me a wonderful introduction for my presentation, quite unintentionally, but nevertheless I do thank him. As you see the title, it's one case study, and these are main parts, so save the time. The object is a container stack site. It's some kind of specific type of structure, a little bit different from bridges, buildings, and other structures. Why? The purpose is quite simple: storing of transport containers, flat pavement, and just that. But what are the problems? First, manipulation needs of the operator, then everyday dynamic changes of the situation. Some containers are removed, some are brought in, and so on. And one particular problem is the multi-level storing. In order to save the area, storage area, all operators put containers on multi-level storing, 4, 6, and even more levels. The container itself is lying on the so-called corner castings. We can see it in the large picture and on the right enlarged. These hollow parts are intended for supports and also for crane lifting, for fixing, anchoring, and so on. So they use as supports. Since the stack sides are wide, flat, they're exposed to severe winds. Many stack sites are near seaports, and that's even worse. So, wind action on such sites can be very, very critical. In case of collapse of some container stacks under wind, the staff which works there can be in very high danger. And so every single stack site has to be considered about wind action, and every location is specific, as we know. In this research, one specific container has been analyzed, and the motivation was one accident on one such site, where operator decided to order some study so that can be sure that the site will be safe, and to possibly introduce some kind of warning system based on anemometer and some alarm system that will, in case of some critical wind velocity, the stuff can be removed from the stack and the containers are left to the wind. Second goal, second reason was to determine eventual need for anchoring the containers. Namely, in common practice is that containers are just put on the ground, and some are put above and above and above without any fixing, any anchoring. In some cases, especially on ships, they are anchored with some chains, with heavy ballasts, and so on and so on. And the third reason is to, for the operator to consider to alternate the orientation of the containers regard to the main wind direction on that site. Problem was that there are numerous stacking combinations. There is no order, there is no some established pattern on every site. So in this research we had to narrow the selection, and you can see on this scheme what we analyzed. 4 cases with 1, 2, 3, and 4 levels of storing. And to further narrow the research, we considered only empty containers, as they're more vulnerable to wind action than the full ones. Wind direction was treated as acting on the largest area of the containers, and unsafe conditions that were analyzed were potential sliding and potential overturning. Wind action was applied on windward and leeward sides. Lateral sides were excluded because they anneal each other. They act on opposite directions. But wind suction on top side, on the roof of container, could lift the object, the container, and it could reduce the friction force. But in this case, we neglected that because it simplified the research, And also the containers have a pretty large mass, almost 4 tons, as you can see, so we excluded that. The container type is high cube, the largest one from the possible standard containers that are present on the market, and here are their dimensions. Wind intensity was calculated standard by Eurocode. Sliding and overturning are different phenomena considering the genesis of their arising, so they had to be calculated separately. And all cases were analyzed in 2 so-called modes. The safe mode, standard one for design, where we applied safety factors used from Eurocode, and the purpose of this mode was to get some kind of velocity database, wind velocity database for that site in order to safely operate. The limit mode, second mode, all safety factors were excluded or set to 1, and this was a referent. We wanted to see what were the critical wind velocities where sliding or overturning should theoretically occur. The sliding check was simple, comparison of wind force and resisting force generated by friction. The overturning check was comparison between overturning moment from wind and stabilizing moment from container weight. Regarding the friction, we had 2 types of contacts. The bottom container lying on the concrete pavement had a friction coefficient of 0.6, and the container that lies over another container, in that case we have steel over steel friction coefficient of 0.4. The important fact is that this multi-level storage can generate many different collapsing scenarios. And that happens even in one single stack case. And I here gave one example. I will not read everything, but 4 levels, if you have 4 levels, it generates 8 subcases of sliding or overturning. And they are listed here, as you can see. So all of them had to be analyzed, and the number of calculations rises. It was done simply by MS Excel. This table presents a preview of the results, giving critical wind velocities for the safe mode and for the limit mode. On the left column is storage scheme with 1, 2, 3, and 4 levels. And here we have cases and subcases. 1 level, only 1 subcase, but 4 levels, 4 subcases. And here is the results, and the results for the limit mode. And in this column, we have the collapse mechanism that happened for that calculation. Sliding over ground, overturning, and so on and so on. In conclusion, after the calculation, we observed that critical wind velocities for the limit mode are normally higher than for the safe mode. It's expected. But the difference are not uniform. They range from 33% for case A44 to 112% subcases which are listed here. Second, greater stack height gives lower critical wind velocities, logical and expected. But the drop in critical wind velocity is regular for the limit mode, but it is not regular for the safe mode. Also, in the limit mode, overturning collapse occurs at lower wind velocities within one storage case, especially for 3 and 4 levels. But in the safe mode, this is not the case. Even inverted behavior is observed. We can go back. So here, 4 levels, and we have 4 subcases. The critical wind velocity almost rises. It's equal but rises, but for the limit mode, it drops almost regularly. So different behavior. As a conclusion, or several conclusions, we can say that difference of critical wind velocities in the safe and the limit mode indicate that possibly Eurocode safety factors are over-conservative. Also, limit mode shows more regular pattern of critical wind velocities when stack height is varied, and also when we consider only one single subcase. Finally, both these conclusions suggest that application of some more sophisticated methods should be used, like contact analysis and finite element method, and also the computational fluid dynamics combined with the fluid structure interaction. At that moment, I can say that one such investigation is in progress, and we hope that we will have soon the results. Thank you.
Thank you, Professor Vatsev. It's really interesting problem that you analyzed. You were good with the timing, so we can have a questions, so we can take questions.
Maybe I should go.
Oh, it's okay. So
course.
if you have a questions,
I maybe have a comment, if I may.
yeah, please.
So you showed with this safe mode that the wind of 8 meters per second will result in overturning or sliding the container.
Yes?
So I find this wind speed very low, because for all the sailors here in this room, if there are any, this is a very light wind, which is everyday wind on the coast, where usually these containers are stored. So from this conclusion, I would say that these accidents would occur on daily basis.
Yes, that is a very logical question. But I didn't hear you. Do you mean the container sites on the land or on ships?
This is a very light wind that...
Yes. But do you mean stacks on land or on ship deck?
On land, I'm
On
referring
land.
to this
Okay,
number.
Okay. That seems very low. Very low. You mentioned that it is for the safe mode. I also doubt about the safe mode, and that was our conclusion. We think, after this investigation, that the safe mode gives over-conservative, so very low values. There is a significant difference between critical modes. And some investigation using CFD that we are doing now show that the differences are even higher. But we could not avoid the safety factors given from the Eurocode. Nevertheless, some tables, some literature data gave very similar critical wind velocities like this one, 10 meters per second, from some other sources. So we are not the only one that received such results. But it is very low. It is not, it's not a storm.
Thank you.
Yes?
So we have our next presentation from Goran Milutinovic, Rade Hajdin, Ivana Andrijašić, Miloš Milosavljević, and Marko Bajić. Goran Milutinovic will present overview of bridge traffic loads in Serbia using BVIM.
Thank you. So my name is Goran Milutinovic. I'm a PhD student at the University of Belgrade, and I'm also, parallel with that, I work as a bridge designer in a company called DB Engineering in Belgrade, Serbia. So today I will talk about overview of a bridge traffic loads in Serbia using bridge way in motion system. This is a paper that we wrote, Professor Hajdin and I, with colleagues from bridge owners in Serbia, Putevi Srbije. So first, what is BVIM, Bridge Way in Motion system? This is a system where the bridge is applied as a weighing scale to determine the vehicles on the bridge and its axle weight and axle spacings, as well as the time of the passage, speed, as well as the lane in which it passes the bridge. So this is a picture of the BVIM system that was installed in Serbia by Putevi Srbija. They purchased the system from a Slovenian company Cestel, and they did locations. They did measurements on 70 locations throughout Serbia with duration of 14 days each. So a little bit about the BVIM system from the Cestel Slovenian company. On the figure on the left shows a schematic view of the system where there is main sensors, temperature sensors, cabling, data acquisition system, and external router to send data. And basically by mounting let's say simply the strain gauges on the bridge superstructure and measuring the strain, by this system it is possible to determine which vehicle is on the bridge and make a record of the traffic from which you can completely reconstruct the real traffic. So on the figure on the right is shown the so-called BVIM algorithm, showing simply how they find out what vehicle is on the bridge. I is the observed influence line. A is the unknown axle load. Then in the equation below G is the bridge response, the sensor response, and M is the number of times the record has been made. So there's the sampling rate of this system of 500 samples per second, and if vehicle is crossing a bridge for a couple of seconds, then they get a number of equations 2 orders of magnitude larger than the number of unknowns, the axles, and they, by some advanced mathematical tools, they are able to find out the unknowns, the axle loads. What's also interesting is they use the observed influence lines and not the theoretical influence lines. The figure on the left, using the same algorithm from the previous slide, and using the large number of random vehicles, and of course knowing that some points on the influence line, this for example the 3-span bridge and influence line for the bending moment in the middle where the sensor is located, they're able to make the real influence line. And why there's a difference between theoretical and observed influence line is that for probably maybe the bearing was theoretically you can assume it's a pin, but it's actually a semi-fixed connection there is a soil pressures, maybe restricted movement of the expansion joint, and similar things that make the real behavior of the bridge. They're also on the figure on the left. Well, the figure on the left, they're also able to separate the dynamic and the static component of the measurement. So as vehicle is crossing the bridge with some speed, of course it will make some dynamic effect, and the dashed line is the static component, and the solid line is the dynamic component. You can see it's oscillating about the static effects, and basically, simply saying they set a cutoff frequency. All frequencies that are higher than those are the dynamic component, and they're eliminating, and what's left is the static component, and then based on that, they're able to say what is the static weight of the vehicle, and and that's basically what user want to have the static weight of the vehicle on the bridge. So until now I was talking about the system. From now I will talk about the measurements that were done. So Putevi Srbije, bridge owners in Serbia, they carefully planned the locations of the measurements, geographically covered the entire country from Zrenjanin to Pirot, and they monitored freeways and highways, different type of the roads. And now we did some preliminary numerical and graphical statistical representation of the main parameters that affect the response of the bridge due to traffic. So the upper table is the truck rate on several locations. So basically the percentage of the trucks in the total traffic ranging from 10 to 20 maybe. And then on the lower side there is numbers of the vehicles in the slow and in the fast lane, which also can be interesting for the response of the bridge. Now this is GVW, gross vehicle weight. So on given here is the histograms of gross vehicle weight on 4 locations, on 4 stations. And you can see maybe 3 modes, three most frequent values, just above the 3.5 ton, which is the limit for the heavy vehicles. And there is no, in this database that we are describing, there is no vehicles lighter than 3.5 tons. Then the next most frequent value is around 150 kilonewtons, and then also just below the legal limit for the routine traffic, around 400 kilonewtons. 400 kilonewtons, and after that there is a sharp drop, as we expected because of the legal limit. Next parameter that is important is number of axles. Again, 4 histograms from 4 measuring locations. Most frequent number, the most frequent truck is a 5-axle truck, and we noticed that on a freeway, there is no, the 5-axle truck is definitely the most frequent one, and on the local roads, there's also a lot of 2-axle truck, which might be expected because of the local traffic and because of the local traffic, smaller vehicles are more frequent. Another histograms for the axle spacing. So again, the most frequent value is the tandem spacing. Now the axle weight. The most frequent value is usually around 75 kilonewtons for a single axle, and there's again, you can see a sharp drop after the legal limit of 113 kilonewtons. And again, the last histogram that I have is for the speed, and usually those vehicles are running most frequently with the 80 kilometers per hour. So why this is all these statistical representations were important? Because these are these measurements that exist. It's very good that they exist, but they're small. They're short term, and for example, in some countries, for example, in Switzerland, they're much longer term. I know they have measurements that last for 20 years on 10 locations, and when you have that type of data, it's much easier to do some probabilistic study. And in this case, you need to somehow scale up, do some simulations of a traffic, and because the final goal of this study is to determine what would be the appropriate traffic load model for the existing bridges in Serbia. So in order to do that, we need to do some traffic simulations to extend the time range of the measurements. So just as a background for all of this, Serbian police as a public information provided information about the registered vehicles that exist in the registry, and on the left it's number of vehicles per year regarding all vehicles, regardless of the gross vehicle weight, and it can be seen that there is like 40% of the traffic growth, 40% more vehicles on the Serbian roads, registered vehicles, as we probably see by the traffic jams in Belgrade, for example. On the right side, again, the very similar chart, but now regarding in specific gross vehicle weight ranges. And what's maybe more very interesting for us is the range between 30 tons and 44 tons. Basically, those heavy vehicles, and it almost doubled in 10 years. So all these two charts are basically some guidance for regarding the traffic growth, and with the final goal of setting up the traffic load model for existing bridges. So, as a conclusion, we provided overview of the bridge weigh motion measurements that were done in Serbia, and for us they represent a solid basis for the probabilistic study that we are currently doing for the optimum traffic load model for existing bridges in Serbia. And what is the main advantage of these measurements for us is that we can reconstruct the whole traffic during that period of measurements, and we are able to capture the simultaneous occurrence of heavy vehicles on the bridge on one location at the same time in different lanes. And the histogram that we showed will allow further simulation of traffic loads for the study that we are doing. So that will be all, and I'm open for any question.
Thank you very much for this nice presentation and keeping in time. Are these systems permanently installed in Serbia?
Excuse me?
Are these systems permanently installed in Serbia on the bridges?
Yes. They bought a system, and then there was initially there was all these measurements that we showed. They are on. They were done on 70 locations, and since then they installed it on one location. It's now continuously recording.
Yeah, these are very important data that can be used in many ways, also for design of fatigue, especially in steel bridges. Any questions from the audience? Thank you very much.
Okay, so we are slowly coming to the last presentation for this session. It's with the title Dynamic Behavior of Reinforced Bridges under Moving Load a simplified numerical and analytical approach. The authors are Dejan Janev, Tony Rangelovski, Darko Nakov, Goran Markovski, and Peter Mark. The presenter is Dejan Janev.
Почитувани председавачи, почитувани присутни, како еден од авторите на трудот со наслов Динамичко несување на армирано-бетонски мостови при подвижни натоварувања, поедноставен нумерички и аналитички метод. Најпрво ќе започнам со можните начини на разгледување на динамичкото несување на армирано-бетонските мостови. Постојат неколку начини, каде што првиот е со испитување со пробно товарење, вториот е со нумеричка анализа на интеракцијата возило-мост и третиот е преку аналитички пристап, со тоа што без разлика кој пристап да се избере, се следи одреден одговор на конструкцијата, каде што во конкретен случај тоа е динамичкиот коефициент кој што го разгледуваме. Динамичкиот коефициент покажува за колку пати ќе се зголемат влијанијата добиени од статичкото дејство на товарот, односно тоа е параметар кој што ни обезбедува важни информации за проценка на состојбата на постоечките конструкции, како и при проектирањето на нови мостовски конструкции. Тековната рамка на истражување е поделена на 4 дела, каде што првиот дел ја дефинира програмата за динамичко испитување со пробно товарење, вториот дел разгледува нумеричка анализа, односно ја разгледува интеракцијата помеѓу возилото и мостовската конструкција, третиот дел е креирање на база на податоци и четвртиот дел е анализа на податоци со аналитички пристап. Кај првиот дел во однос на креирање на програмата за испитување со подвижен товар, најпрво треба да се утврди состојбата на мостовските конструкции, односно во каква состојба се наоѓа конструкцијата пред да се изврши испитувањето на истата. Потоа се дефинира пробниот товар, односно се дефинира какво возило ќе се користи, колкав ќе биде бројот на оските на возилото, меѓуоскиното растојание, брзината на движење на возилото, како и тежината на самото возило. Исто така, од аспект на возните карактеристики на возилото се дефинира брзината на движење и траекторијата по која што ќе се движи возилото на мостовската конструкција за време на испитувањето. Следен чекор е определување на мерни места кои што ќе бидат поставени на конструкцијата, како и мерна опрема која што ќе се користи за време на испитувањето, со тоа што најчесто се одбираат критичните пресеци на мостовската конструкција, каде што го очекуваме максималниот одговор кој што го разгледуваме и ни е од интерес. По завршување на испитувањето на конструкцијата се преминува на обработка на резултатите, користејќи соодветни техники за обработка на сигнали, со цел да се добијат максималните динамички и статички одговори. При нумеричката анализа даден е диаграм на тек, кој што ја опишува самата анализа, со тоа што за извршување на анализата користен е модулот OpenSysPy во Python, кој што представува модул за нумеричка анализа со конечни елементи. При самата анализа најпрво се дефинира моделот на возило, подоцна се дефинира моделот на мост, се врши интеракцијата помеѓу возилото и мостот, се врши дискретизација на двата модели, подоцна се дефинираат динамичките равенки на возилото и на мостот, односно на нивната интеракција и се преминува кон решавање на динамичките равенки. И на крај се врши интерпретација на резултатите. Најпрво се дефинира моделот на воз, односно се дефинираат карактеристиките на возилото, како што се масата на возилото, крутоста и придушувањето на системот на суспензија, бројот на оски и оскино растојание, како и почетните услови на возилото, односно почетната местоположба, почетната брзина и почетното забрзување. Во литературата се дадени неколку карактеристични модели на возило кои што може да се применат, од кои што во конкретниот труд е применет последниот модел кој што представува подвижна осцилаторна маса, како што е дадено на најдолниот график од слайдот. Потоа се дефинира моделот на мост, се дефинираат карактеристиките на мостот, односно се дефинира масата на мостот, крутоста и придушувањето на мостовската конструкција, статичкиот систем на конструкцијата, како и геометријата на конструкцијата, бројот на распони, должината на самите распони, ширина на мост, висина и рапавост на подлогата на асфалтната конструкција. Потоа се дефинираат граничните услови кои што пред се зависат од статичкиот систем и се дефинираат почетните услови на мостот, односно почетните вертикални деформации, почетната брзина и почетното забрзување кои што на почетокот пред да навлезат возилата на мостот се еднакви на нула, односно се смета дека конструкцијата мирува пред да навлезат самите возила. Овде на првата скица е прикажан дискретизиран модел на конструкцијата, односно поедноставен линиски модел, кој што е добиен преку модулот OpenSys-Pi и дополнително е даден приказ и начин како треба се земе во предвид рапавоста на подлогата и интеракцијата помеѓу подлогата и самата конструкција. Рапавоста на подлогата може да биде определена на два начини. Едниот начин е преку експериментален пат, односно да таа да се добие со испитување на подлогата. Вториот начин е математички, односно преку примена на случаен Гаусов процес. На графикот каде што е прикажана рапавост на подлогата може да разгледаме опсек од многу добра до многу лоша состојба на самата подлога. Кога започнува нумеричката анализа на интеракцијата помеѓу возилото и мостот, најпрво се врши дискретизација на моделите, потоа се дефинира вкупното време кое што е потребно возилото да помине преку мостот и временскиот чекор според кој што се врши анализата, се определува влезот и излезот на возилото од мостот со тоа што се користи хевисайдовата функција на чекор. Карактеристично за оваа функција е дека ако ја разгледуваме координатата на осовината на возилото, која што е дадена како x, ако вредноста на x е поголема од 0, тоа значи дека функцијата добива вредност од единица и ни укажува дека возилото се наоѓа на самата конструкција, односно ако вредноста на координатата x е помала од 0, тогаш функцијата има вредност 0 и укажува дека возилото веќе е излезено и е надвор од самата конструкција. Потоа се дефинираат динамичките равенки на интеракцијата помеѓу возилото и мостот и се користи Нюмарк бета методот за решавање на нумеричката анализа. Овде се прикажани неколку резултати каде што како одговор на конструкцијата е разгледувано вертикалното поместување, со тоа што на првиот график може да се увиде ефектот кој што се јавува кај вертикалните поместувања кога разгледуваме влијанието од придушувањето на конструкцијата, односно со црвена испрекината линија е прикажано кога придушувањето на конструкцијата не е земено предвид, односно со сина линија прикажано кога тоа придушување на конструкцијата е земено предвид, додека на двата десни графици е прикажано влијанието од крутоста на потпорите. Првиот десен график го презентира моделот кога лежиштата се разгледуваат како апсолутно крути, додека вториот график го зема влијанието, односно ја зема крутоста на лежиштата. Не напоменав дека за време на нумеричката анализа се направени повеќе од 27.000 разгледани случаи, со тоа што се разгледувани гредни мостови со статички систем проста гред. Откога ќе се заврши со нумеричката анализа, се преминува кон креирање на база на податоци. За креирање на базата на податоци се разгледуваат 4 клучни критериуми. Првиот критериум е состојбата на горниот строј на мостот, односно состојбата на коловозната конструкција на самиот мост. Потоа, како втор критериум се карактеристиките на самото возило, трет критериум се материјалните карактеристики на конструкцијата и четврт критериум се геометриските карактеристики на конструкцијата. Дел од овие параметри кои што се наброени во оваа база на податоци се влезени во самата анализа. Откако ќе се креира базата на податоци, се преминува кон аналитичко толкување на резултатите кои што се добиени со самата нумеричка анализа. Најпрво се врши графички приказ на промеливата и одговорот како 2D графици со цел да се види влијанието на секој параметар поотделно, потоа се врши филтрирање на самите резултати и селектирање на податоците, па се преминува кон повеќе кратна линеарна регресија каде што се разгледува методологијата на површини на одговор со цел да се добијат полиномни равенки и кои што ќе служат подоцна за предвидување на самиот одговор на конструкцијата кој што го разгледуваме, односно ќе се креира така наречен сурогат модел. Овде се дадени неколку графици каде што е прикажано дводимenzionално одредена променлива и одговорот на конструкцијата. Од ваков тип на графици не можеме да дојдеме до некои конкретни заклучоци и затоа се преминува кон методологијата на површина на одговор. Методологијата на површина на одговор е збир од статистички техники кои што се користат за креирање на сложени системи со цел да се моделира и анализира одговорот на системот при различни влезни податоци. Ова методологија на површина на одговор е составена од дизајн на експеримент, каде што се утврдува влезниот број на параметри и кои параметри ќе бидат вклучени во самата анализа, потоа се преминува кон регресиска анализа за креирање на полиномни равенки, се разгледува анализата на варијансата со цел да се одреди кој параметар има најголемо влијание во самиот модел, се врши оптимизација со цел за одредени влезни параметри да се открие посакуваниот одговор, односно да може да се коригираат влезните параметри. На крај, оно што е најважно е да се направи валидација на самиот модел со цел да се утврди колка ќе биде точноста на предвидување на самиот систем. На овој слайд се прикажани 4 површини на одговор, кои што се како променливи се фиксирани брзината на движење на возилото, како и распонот на конструкцијата, а како одговор е динамичкиот коефициент. Промената на површината на одговор се врши од причина што останатите параметри кои што се влезени во моделот варираат од минимална до максимална вредност, а со тоа се променува и површината на одговорот. Откако ќе се добијат полиномните равенки од методологијата на површина на одговор, се преминува кон анализа на чувствителност на системот, со тоа што како метода која што е користена е методата на Собол индекси. Методата на Собол индекси најпрво ги дефинира влезните параметри и нивната распределба, потоа се генерира сет од податоци користејќи ја Монте Карло методата, се врши процена на одговорот на моделот за секој влезен примерок, потоа се врши декомпозиција на вкупната варијанса за секој променлива со Собол индексите, се врши пресметка на вкупните индекси и на поделните Собол индекси и на крај се врши толкување на резултатите. За 4 возила кои што претходно беше креирана површина на одговор, тоа се возило со 3 осовини, возило со 4 осовини и 2 возила со 5 осовини, каде што имаме различно растојание помеѓу осовините и различна прераспределба на товарот по осовини. Од овде, преку Собол индексите од прв ред, може да се види влијанието за секој параметар поотделно, додека преку индексите од втор ред се гледа влијанието на интеракцијата помеѓу различни параметри. На крај може да се заклучи дека по спроведувањето на анализата и добиените површини на одговор се забележува дека при исти влезни податоци, како што се брзината на движење и распонот на конструкцијата, се добиваат различни површини на одговор, доколку по мостовската конструкција се движат различни возила со различен број на осовини и различна прераспределба на тежината на оски. Од анализата на чувствителност може да се заклучи дека одредени параметри имаат значително влијание, како што се тоа се распонот на конструкцијата и брзината на движење, додека ако го земеме во како пример модулот на еластичност на бетонот, може да се констатира дека неговото влијание е занемарително и во полиномната равенка истиот тој параметар може да се замени со неговата средна вредност. Покрај овој заклучок на индексите од прв ред се забележува дека кај Собол индексите од втор ред, кои што ја разгледуваат интеракцијата помеѓу различните влезни променливи, најголемо влијание има интеракцијата помеѓу распонот на конструкцијата и брзината на движење, додека останатите интеракции имаат помало влијание и исто се препорачува овие членови од полиномната равенка се заменат со нивната средна вредност, со цел да се добие што е можно поедноставен и попрецизен израз за предвидување на динамичкиот одговор, во конкретниот случај тој е динамичкиот коефициент. Ви благодарам на вниманието.
Okay, thank you very much, Dan, for this interesting presentation. Now we'll have 2 questions. Are there any questions? Yeah, we have one question there. So please give the microphone.
Да ве прашам, дали може да се каже нешто повеќе за оскултационата опрема? Опремата која ќе користи делатометри и генерално за влезните податоци.
Во конкретниот случај користени се како влезни податоци покрај резултатите од испитување, користени се и резултати од нумеричка анализа, така што е направена комбинација. Во однос на мерната опрема, зависно од тоа која вредност сакаме да измериме, користени се како мерна опрема за мерење на вертикални деформации, тоа се угибометри, во конкретниот случај дигитални угибометри, дата логер соодветен за запишување на податоците и за мерење на дилатациите користени се електрополимерни ленти.
Okay. Do we have a second question? No. Okay, thank you very much, Dan. At the end, I would like to thank all the presenters for the nice presentations. We are only 1 hour late, so I want to remind everyone that next we have the roundtable, which is on the title Current State and Trends of Structural Engineering. So we are awaiting everybody to take a part on this event. Once again, thanks to everybody, and maybe our president would like to say a few things.
Океј, јас ќе зборувам на македонски.
Okay.
Ќе ве замолам сите да останете, значи да не ја напуштаме просторијава. Ќе биде брзо, така е ветено за неколку минути. Сцената ќе се премести во форматот во кој што треба да биде и продолжуваме веднаш. Значи, please stay on your seats.
In this room, yeah.
Few minutes.